Hey guys, today we are going to finish up our notes for this chapter, specifically focusing on kinetic and potential energy today. So before we get into those two specifically, let's just talk about what energy is in general. Energy is the measure of the ability of an object or a system to perform work. Basically, again, if we're with a system or if an object, something that we're looking at has the ability to do work, it has energy. So we can measure what that energy is in a bunch of different ways, and we have a lot of different classifications of energy. The first one being kinetic energy, which is energy of an object due to its speed. So if an object is in motion, it has kinetic energy. We have specifically gravitational potential energy, which usually I'll just generalize this to potential energy. There are different forms of potential energy, but these two specifically are the ones that we focus primarily on. When I say potential energy, just know that that means gravitational potential energy, which is energy that's stored. So potential energy is energy that's stored in an object, so it's just readily available to do work. But in this case, gravitational potential energy, just like it sounds, is the ability of an object to do work based on its position in a gravitational field. So if it's sitting on a shelf, if you're holding it up, ready to release it, as soon as that support or that force stops acting on it, it has the potential to do work and have that object be displaced and travel a distance. So the higher the object is, the greater the potential energy it has to be released based on how far it has to fall, basically. Some other forms of potential energy. Elastic energy is energy that's stored in an object when it's either stretched or compressed. So think like a rubber band or a spring. Both of those are elastic energy. Again, if you stretch a rubber band, it's got a whole bunch of potential energy stored up in it, so that as soon as you release it and you stop acting on it, that force stops acting on it, then it's going to release that potential energy that it has stored up. Or if you compress a spring, again, that spring is going to release a whole bunch of energy as soon as you stop acting on it. We also have chemical energy. Chemical energy is, again, energy that's stored in chemical bonds. So this one, a lot harder to see, a lot harder to categorize. But again, like literally the bonds between the atoms and the molecules has energy stored in it, so that if you break those bonds, a bunch of energy is going to be released. Nuclear energy, again, very similar to chemical energy, but the energy now is stored within the nuclei of the atoms. So if you were to destroy those the nuclei, the actual nucleus of the atom, then you would be releasing energy there as well. There's more than that as well. There's also light energy and there's heat energy. Again, energy that's released in the form of heat or in the form of light. So that's another option as well. I know we talked about that back with like those Sankey flow charts that we looked at in the last set of notes, where some of that energy was released as heat or some of it was released as light when we're looking at those, the kind of the power flow diagrams. So work, when work is done, energy is transferred from one form to the other. It might be gravitational potential energy is gained as you increase the position in the gravitational field. It could be kinetic energy that's, again, being gained or being lost as that object changes its speed, it's changing its velocity. Light energy, again, when you flip a switch on, that light energy is being released, and that has to come from somewhere. Heat and sound, that's another one. Sound energy, which we'll get into. We'll see, depending on how the semester goes. We're quite a bit behind this year with everything going on. But again, heat and sound are released when you apply the brakes of your car. Just like with matter, energy is conserved. And just like momentum as well. Momentum is always transferred from one to the other. We have a conservation of momentum in a closed system. Here, energy, even more so, energy just like matter, is conserved, which means it cannot be created, it can't be destroyed, it's only being transferred from one form to the other. In other words, total energy of a system is conserved, meaning that if we, again, without putting extra stuff into the system, so if we just have a closed system, that energy stays constant. So if we have a bungee jumper, the gravitational potential energy that it has available to it, as soon as it jumps, that that gravitational potential energy gets converted into kinetic energy because it's going to be gaining velocity, so it's going to be increasing its kinetic energy. But as it jumps down, like as it falls down, that potential energy, that gravitational potential energy, is going to decrease because it's lower and lower in the gravitational field. It has less space to fall, so therefore it has less potential energy. And then as you get down to the bottom, and that bungee cord, that bungee rope, if you want to call it a bungee rope, starts to stretch, that's converting it into elastic energy. It's got all that energy stored up, and then as soon as it gets to the point where it can't stretch out any further, then it's going to be released back into kinetic energy, moving, accelerating the bungee jumper back up. And then as you're increasing that height, you're starting to slow down because of gravity pulling down on you. And then as you move up, it's increasing that gravitational potential energy. So it's just kind of this ebb and flow back and forth of converting between all these different forms, which is kind of cool. So gravitational potential energy, like I said, it's energy of an object due to its position in the gravitational field. So the higher it is, the more potential energy it has to be released. The lower it is, or if it's all the way on the ground, it has no gravitational potential energy. We've got some different ways of writing it. You can see here GPE, which, again, I usually just say PE, potential energy. If I just say PE, just assume that this is the one I'm talking about. Similar to like if you remember our free body diagrams from first semester, our force diagrams and stuff, we have our force due to tension or our force due to gravity. We can have the same thing here. This is energy and then subscript P for potential, or energy due to gravity. Again, I usually just use PE as the abbreviation. In this set of notes, I'll use E sub P a lot. But I kind of those are my two main ones that I use. Potential energy is based off of three things: the mass of the object, the height of the object, and the force acting on the object due to gravity, so the gravitational field strength. So our formula for gravitational potential energy is just multiplying those three things together: the mass of the object, the gravitational pull, G, and then the height of the object, H. MGH, mega, is how we calculate potential energy. Just like with our momentum that we looked at earlier this chapter, we don't traditionally have our mass changing, or we're looking at our change in momentum. It was almost always due to a change in velocity, because that mass is most of the time remaining constant. So if I wanted to change the momentum, I had to change the velocity. Kind of the same idea here with anytime we have a change in potential energy, our mass is not going to change for that same object. The gravitational pull is not going to change, because we're not going to be exchanging what planet we're on and experiencing a different gravitational pull. It's going to be because of a change in the height of that object. So again, this is our formula for a change in potential energy, and really it's just focusing in on saying, all right, if I have a change in height, that's what's going to change our potential energy, or vice versa. If I see that there's a change in my potential energy, I could work backwards to figure out what that change in the height was. So let's go ahead and take a look at an example problem here. So in this problem, a supermarket employee lifts a baked bean tin weighing 250 grams from the floor to a shelf 2 meters high. How much gravitational potential energy does it gain? And here we're using our standard 9.8 newtons per kilogram, meters per second squared, for our gravitational pull. So looking at our formula, we know, again, we're looking at how much potential energy is gained, right? So we're increasing that potential energy, not just calculating the final potential energy. We're looking at how much it's gaining. We would be taking mass times gravity times the change in height. So in this case, our mass should be measured in kilograms. Since this was given in grams, we need to convert that into kilograms by moving it over 3 decimal places. So 0.25 kilograms. Our gravitational force, G, is 9.81. And then that change in height, we're gaining 2 meters. So that's why we're using a positive 2. If we had a loss, if we were taking it from the top shelf and putting it down to that bottom shelf, we would be losing 2 meters. So we'd use a negative 2, and we would have a negative change in potential energy. which is something that is possible we might see eventually. So if I just multiply those together, 4.9, and then joules is the unit. Just like with work, joules should be our unit. Take a look at another one. For example, number 2, we have a pole vaulter that has a mass of 80 kilograms, jumps to a height of 5 meters. What is his gravitational potential energy at the highest point of the jump? So here, just our regular old equation for potential energy. We're just looking at the very peak of that jump. What is the maximum potential energy that this pole vaulter has? So our equation, mass times gravity times the height. So we're just going to go ahead and plug in our 80 for our mass. Gravity, again, we're still on Earth, so 9.81. And then the height is already given in meters, so times 5. So we have a whopping 3,924 joules would be how much potential energy the pole vaulter has at the peak. Kinetic energy, kind of the flip side of that, if potential energy is kind of the ability for work to be done eventually, where it's stored up, kinetic energy was what we see when that energy is released. So when an object is moving, it has velocity, we can figure out what its energy is, kinetic energy. Here is our formula for it. Again, it's involving our mass, and here, since we're talking about it being in motion, the velocity is the other aspect of that equation. A little bit different, it's a little more complicated. It's not just multiplying them together. Our equation for kinetic energy is 1/2 mass times velocity squared. 1/2 mass times velocity squared. I'll use both of these interchangeably. Again, KE for kinetic energy, or E sub K for energy that is kinetic, is what I just abbreviate to. Here in our equations, kinetic energy, again, is measured in joules, just like all of our energy is. Mass, standard unit is kilograms. Speed, or velocity, standard unit is meters per second. So, again, just take our velocity, square it, multiply it times the mass, and divide by 2. So in a system, any kind of resistive force, such as friction or air resistance, we're going to ignore those unless explicitly stated. So in most cases, again, we're going to kind of deal with the ideal version of the problem. If we assume that none of those resistive forces are acting on our object, if we just have our object increasing velocity, so gaining kinetic energy, or again, we're picking it up and raising it up, so it's gaining potential energy. If we ignore those other resistive forces, any kind of loss of kinetic energy has to lead to a gain in potential energy. Or vice versa. If we're losing potential energy, if it's falling, it's losing potential energy by lowering in the gravitational field. But because of that, it's accelerating, it's moving faster than it was before, so it's gaining kinetic energy. So again, like I had said, if a object has a mass of m, is released from above the ground at a height h, it will gain speed v as it falls. And again, due to the conservation of energy, right? Energy is not created or destroyed; it's just transferred from one to the other. If we assume that air resistance doesn't have any effect on it, a change in that height, falling, would lead to a change in our velocity as well. So this equation is something that we'll have to use quite often when you guys get to that worksheet that we're working on, kinetic energy. It's like KEMPE worksheet, I think is what I have it titled. It's basically our kinetic and potential energy worksheet. We'll utilize this quite often to be able to go back and forth between two different things. So if I know the kinetic energy of an object at some point, I can use that to work backwards to find what the potential energy was. Or usually what's going to happen is we'll be able to calculate that potential energy, because all we need for that really is the mass and the height of the object. That's usually the easier one to find. If you know what the potential energy is at its maximum, at its max height, that's the highest that the potential energy can ever be, then that is the highest that the energy of the system is going to be. So let's take a look at one of those. For this next example, we've got a ball that has a mass of 400 grams, is thrown upward at a speed of 5 meters per second. Again, we're assuming Earth, so 9.81 meters per second. First, they want us to figure out what is the ball's kinetic energy as it's released. So we're given the mass, we're given the velocity to start with in this case. Again, our kinetic energy equation is 1/2 mv squared. So we'll just plug stuff in there. 1/2 times 0.4. Again, don't forget to convert your units. Our units have to be in kilograms. That's the standard unit for our mass. So 400 grams. Move that decimal place over 3 to get 0.4 kilograms. Our velocity is 5, so we'll square that, multiply it out. We should end up with 5 joules. 5 joules is that initial kinetic energy. Now, at that point, there's no way that our ball, if we're throwing it upwards, our ball, is going to be gaining kinetic energy. There's no way that it's going to increase its speed because we're throwing it upwards. Right? The only thing that's going to happen is it's going to start to slow down, just like we saw back in projectile motion. When you launch it up, as it gets closer and closer to the peak, it's going to start slowing down because gravity is pulling down on it to try and stop it. So if we work backwards and be able to figure this out here, the second question that we're being asked is, what's the ball's maximum gain of potential energy? Which, if this kinetic energy, 5 joules, is the amount of kinetic energy we have initially in the system, and that's the biggest your kinetic energy is ever going to be, we know that any change in potential energy has to be equal to that kinetic energy. So if our kinetic energy is 5 joules, our potential energy has to also be 5 joules. Now this next part is the cool thing, because if we know what that velocity is, or what that speed is, in this case the kinetic energy of the ball when it's released, we can actually use that to figure out what the maximum height was. This is something that we kind of did a backwards way of doing it, with looking at the forces and the exit velocity and the angles and stuff back in chapter 2. But we can actually use our kinetic and potential energy equations to do the same thing. Here, if I'm trying to find the maximum height of the ball, I'm going to use the fact that I now know that the maximum potential energy is 5 joules. And I know the maximum potential energy happens at the peak of the trajectory. As the ball flies up in the air, the highest point is the maximum potential energy. So I can use that equation. My potential energy is equal to mass times gravity times the height, and plug in everything that I know. Now here, I went through and solved for h first, since I'm looking for that height, which really just divided by mass and gravity on both sides. You can do it however you want to. Again, plug stuff in and then solve for h is probably how I would do it, just to get our numbers in there first. But you can rearrange it first and then plug stuff in. So we know that our potential energy was 5 joules, our mass was 0.4 kilograms, and then our gravitational pull again is 9.81 meters per second squared. So you multiply those out, and we should end up with 1.27 meters. For our last little bit here, resistive forces. We know resistive forces, again, we talked about friction, we talked about air resistance, we talked about a bunch of other resistive forces as well. They're forces that act on a moving body in the opposite direction of the movement. Friction is the big one that we've talked about, which includes drag, air resistance, all of those different types of friction. They're working against the movement of that object. So if we have an object like a roller coaster or something similar to that, that's moving vertically without any kind of driving force, we know that if my change in potential energy and my change in kinetic energy are not the same, any discrepancy between those two things, right? If we're gaining kinetic and we're losing potential, but they're not happening at the exact same rate, that tells us that we're not dealing with that ideal world that we were pretending to live in before, where we ignored those resistive forces. If we have friction happening on our object, we would know that that's happening based on this formula here. So W here is work done against the resistive forces. Basically, this tells us how much resistive force is acting on it. Here, our change in potential energy plus our change in kinetic energy is how we would figure that out. Now, this equation is not going to be, well, they're not going to both be positive, because if we know that if one is going up, the other one's going down, right? If I have a positive change in kinetic energy, if I'm gaining kinetic energy, that potential energy is going to be negative because it's going down, or vice versa. If I'm losing potential energy, if I'm losing kinetic energy, if it's slowing down, again, vertically acting, that would be a gain in potential energy, that would be positive. So if we add those two things together, if they're not a perfect balance, if this doesn't add up to zero, where, again, the gain and the loss is identical, any discrepancy between those two, then we can attribute to those resistive forces. Okay, that is all we've got for today. That is the last part of our notes here. Your homework that you guys will be working on tomorrow is, again, that kinetic and potential energy worksheet that is posted on Classroom. You guys also should have a hard copy of that still in the packet that I gave you guys at the beginning of the semester. If you guys have any questions, concerns, thoughts, ideas, hopes, or dreams, as always, make sure you guys let me know. And have a fantastic day. We'll see you guys soon.